Okay, in this video I'm going to talk about inverse functions. Now before you watch this video, make sure you've watched the video on composite functions because you need to know about that for me to talk about inverse functions. So let's take a look first of all at what we need for an inverse function. All right, the first thing we need is the whole concept of a one-to-one function. Alright, so now what do I mean by that? Well, let's for a minute talk about functions, right? In order to have a function, you have to have the idea that every x corresponds to only one y. So visually, I mean the picture that you always want to have in your head for this is the parabola, right? Alright, I have a parabola going this way, and I have a parabola going this way. One of these is a function and one is not. And the way you tell is if you take an x and then you can trace that x back to two different y values, you don't have a function. Alright, anywhere I take an x here, it's only going to trace to one y value. Alright, so that's the idea of a function. You have this vertical line test. If the vertical line passes the graph in more than one place, not a function, right? Not a function. Over here, this is a function. So every value of x corresponds to only one value of y. All right, that makes something a function. Now, if we swap that around and look at the y values, if in addition to this I have that every y corresponds to only one x, then I have a function that's one-to-one. So if I look at, I have to get away from a parabola now, but if I look at something like this, alright, now if I look at a y value, alright, each of those y values corresponds to only one x value. Notice that's not true here, right? Because if I look at this y value here, I have one x on this side, and I have another x on this side. Perfectly fine for a function. This is one-to-one. Alright, so the idea here is if a is not equal to b, then f of a is not equal to f of b. Alright, so essentially if I have two different y values over here, they have to correspond to two different x values over here. And the other way around, if I have two different x values over here, they correspond to two different y values here. Alright, now we can use kind of a notation. It's not really a notation, it's kind of a picture to illustrate this in a more general sense, and I like to refer to this as the blob picture. So I have a blob over here, and I have another blob over here. And I have a way of getting from the first blob to the second blob. Alright, so I'm going to call my pathway here f. That's my function. Alright, which would make this blob the domain of f. And this blob would be the range of f. And the idea with the function is I have a bunch of points. Let's do 4 of them. Right? I've got a bunch of points over here, and I've got another bunch of points over here. And f is my way of associating or corresponding every point on this side with a point on this side. Right? Now for this to be a function, let me do something here. Let me change something good, and how about green? Okay, so to get from this point over here, I go through f, and let's say I land there. Alright, this point may land over here, maybe this one lands here, and this one lands here. Alright, so I get all this spaghetti. Alright, going from the domain of f to the range of f. Now every x on this side is going to correspond to only one y, and every y on this side is going to correspond to only one x. Alright, that means that I not only do I have a function, but I have a one-to-one function. And if I have a one-to-one function, that means that I can exactly reverse this process. So if this x only goes to that y, then that y only goes to that x. Alright, and that means that I can make another pathway going back this way that I'm going to call F inverse. Alright, so notation-wise, the inverse of a function f is f, little minus 1 up there. Alright, now be careful. This is not algebraic notation, it's function notation. That does not mean 1 over f. That means f inverse. Alright, and notice, because f inverse is moving in this direction, that this side is the domain, because that's where it's starting. And this side is the range. Alright, so what we get out of this is the domain of f is the range of f inverse. And the range of f is the domain of f inverse. Okay, and this property is actually important. The fact that f goes, let's say, from left to right, and then f inverse exactly reverses that process from right to left. Okay? Alright, so let's take a look at how we can visualize this another way. Alright, I'm going to make a function. I have a function right here. Alright, this function right here is made up of a sequence of points. Right? And the points, if you take a look, I can prove that this is a function by looking at my domain, right? And the domain, or the domain variable, is x. So all of the points are unique. All right, I'm not repeating any values for x. All right, and I'm not repeating any values for y. All right, so this is a function, and it's one-to-one. So I can write out the domain of f. Again, the domain variable is x. All right, so my domain for f are all the x coordinates, like that. And the range for f are all the y coordinates. No, that's not 25, is it? That is 27. Did it again. 8, 27. Okay. Alright, so we have all of our x coordinates, all of our y coordinates, all of our domain, all of our range. Now if I want to construct the inverse of this function, I have to swap the domain and the range. That means that the domain of f inverse is going to be the range of f. So the range, or the domain over here, is that, and then the range of f inverse is going to be the domain of f. Like so. Alright, so now if I want to construct f inverse, I can do so just by pairing up the x and y coordinates, just like I had up here, and I will get this. Alright, so this is f up here, this is f inverse down here. Okay, so let's look at evaluating one of these little functions here. Alright, now if you think about composing a function with its inverse, all right, let's think about what happens here. I'm going to use my little function machine again. All right, so let's look at this first. All right, so I want to compose f inverse inside f. All right, so let's pick a point in the domain of f inverse. So let's pick, I don't know, let's pick -8. All right, so I'm going to take -8 and I'm going to input it into the f inverse function. So when I put -8 into f inverse, what do I get out? Well, I get -2 out. So what comes out of here is -2. That then goes into the f function machine. So here's -2. When I put that into f, what do I get out? I get -8. So notice, -8 went in and -8 came out. Let's look at it in the other direction. All right, so now let's look at this one right here. All right, so that means I'm putting f into f inverse. So I have to find an x in the domain of f. Let's go down here. Let's take 3. All right, so I'm going to put 3 into f. What happens when I put 3 into f? Well, I get 27 out. That goes now into f inverse. All right, so I put 27 into f inverse. What do I get out? I get out 3. All right, so 3 went in and 3 came out. All right, now that makes sense because remember, f and f inverse are just swapping their domains and ranges. So if I pick a value, let's say from f, I pick 3. I put that into f, what do I get out? 27, or -27. All right, I come down here, and now I put that into f inverse. What do I get out? -3 again. All right, so you've got this kind of zigzag that happens, domain to range to domain to range, like that. All right, what this tells me is that when I compose f with f inverse of x, what I get out is x. And when I compose f inverse with f of x, what I get out again is x. All right, now before I get into any more algebra, I want to take a look at a geometric interpretation. What does it mean geometrically for two functions to be inverses? All right, now this little function that I set up here with the points is kind of obvious. I wasn't trying to hide anything. These are really points off of the graph, off of the function f of x equals x cubed, and these are points off of the function f of x equals the cube root of x. Okay. All right, so these are functions we've dealt with before, so I can make a quick sketch here of x to the third, right, which is going to look more or less like this, roughly. All right, so this is y equals x to the third, and I can make a quick rough sketch of the cube root of x, which looks like this. All right, so this is y equals the cube root of x. All right. Now, what's the relationship between the two of these graphically? All right. Well, we can use our graphing calculators to graph the two of these on the same coordinate axis here. All right. So here's my TI-83 calculator. So I'm going to clear this out, and I want to enter in the two functions. So I'm going to put in x to the third in one function, and I'm going to put, now I don't have a cube root, so I'm just going to say x to the, remember the cube root is the 1/3 power, so to the 1/3 power. Alright, now I'm also going to, just to get a better shot, I'm going to restrict my window. Let's say negative, let's do -3 to 3. Just because I really want to close, I really want to close in there. Leave that at 1. -3. Again to 3. I'm not having much luck here. 3. Okay. Wait a second. -3 to 3. Okay. And now I graph that, and let's see what happens. So there's x to the third. Here's x to the 1/3 sneaking in there. Okay. Alright, now it may be a little difficult to see the relationship between the two of them, so I'm going to add one more function in here. I am going to add in, go down here, y equals x. Alright, and notice where y equals x ends up. Right down the middle. Alright, so what we get here is, if I make a new one, I'm going to make a bigger one over here. Make a nice big picture. Alright, so here's the line, y equals x. Alright, and we'll make one, because this is the point that's on all three. Alright, so here's 1, 1. Alright, so here's 1, 1. Here's -1, -1, more or less. Alright, so when I do y equals x cubed, that's coming up like this. Alright, more or less. I'm exaggerating here too, okay? Alright, when I do the cube root, what happens is any point over here is going to land over there. So I'm going to get this. Excuse me. Any point over here is going to land over here, so I'm going to get that. Same thing down here. If I have a point here, it goes here. And if I have a point here, it goes here. Okay? So that's kind of an exaggerated version of what you can see on the calculator. Excuse me. Alright, essentially, y equals the cube root of x is reflected over the line x equals y from x cubed. Alright, so the graphic interpretation of inverses is you have a function f of x, you reflect it over the line y equals x, and you have the graph of the inverse function. Alright? Alright, so let's go back to some algebra. Alright, I have two functions, and I want to verify that these two functions are indeed inverses of one another. Alright, in order to do that, I have to use the idea that I had, was it here? Yeah, over here. Alright, of doing the compositions. Alright, so I need to compose f with f inverse, and I need to compose f inverse with f, and show that when I do that, I get x. Alright, so here are my two functions. I've got f of x is 2x plus 3, and f inverse is 1/2 x minus 3. So I'm going to do it this way first. It doesn't matter which way you do first. I'm just picking this way. Alright, so if you recall from the video on composite functions, what this means, putting a function inside a function, means I take f, and instead of x, I'm putting in f inverse. Alright, so what is f inverse? Well, it's this. Alright, now I have to simplify this. This is all multiplication here, so I can just use the associative rule and put those two together. When I put those two together, I get 1, so then I have x minus 3 plus 3, alright, which is x. So I'm good in that direction. Now I have to check it the other way. You always have to check it both ways because it's possible one way will give you x and the other way won't. Alright, so I compose in the other direction. Alright, so now what this is saying is I start with f inverse. So that means I have 1/2 f of x minus 3. Alright, so that's 1/2. Now what is f of x? F of x is 2x plus 3. Alright, and I can simplify this, right? 3 minus 3 is 0. So that's 1/2 times 2x. And again, this is all multiplication, so I can associate those two. That'll be 1, so that gives me x. Alright, so that says that these two functions, 2x plus 3 and 1/2 x minus 3, are indeed inverses of one another. Okay? Alright, now, you might want to find an inverse. In fact, more often than not, rather than proving that two functions you already have are inverses, you're going to need to take a function and find its inverse. So I thought I'd start with something that we already know the answer to, just so you can see how that works. Alright, so I'm going to start with the function we had on the last page, f of x equals 2x plus 3. And I'm going to find its inverse function. Now remember, the relationship between the function and its inverse algebraically is the swap between the domain and the range. Alright, so the first thing I want to do is I want to write this using domain and range variables. So that means y for the range is 2x plus 3. Then the inverse function is going to have the range of f is going to be the domain of f inverse, and the domain of f is going to be the range of f inverse. So that means I have to swap the domain and the range variables. So range variables y all become x's, and domain variables x all become y's. Alright, then to get the actual inverse function, I just have to solve for the range variable, solve for y. Alright, so I can do that. I can do that pretty quickly with this one because it's just a linear function, right? Subtract the 3 over. Divide everything by 2. Alright, so on this side I get y, which is fine. Over here, just to get it in the same form, remember, dividing by 2 is the same thing as multiplying by 1/2. Alright, and I get that. And if you look back on the last page there, right, 1/2 x minus 3 was indeed the range, the inverse function. So this tells me that f inverse of x is going to be 1/2 x minus 3, which we already knew. Okay, but that's the process. You swap x and y, and then you solve for y. Alright, so let's do it over here where we get something a little more complicated. Again, if I want to find the inverse, the first thing I need to do is, first of all, write it in terms of domain and range variables. So I need a y. Then I need to swap the domain and the range. So that means my range becomes my domain, so that becomes an x, and my domain becomes my range, so those become y's. Like that. Alright, now I have to solve this for y, and I picked this one because the algebra is a little more complicated, and it might be something that you haven't done in a while. Alright, so this is again essentially just a proportion, so I can multiply both sides by y minus 1. So I'll get x times y minus 1 equals 2y plus 1. Alright, I have to multiply this out, so I get xy minus x equals 2y plus 1. Now the key here is, just like solving any equation, I need to group my variables. So I need all my y's on one side. That's the variable I want to group. I want everything else on the other side. Alright, so I can subtract 2y, let's move this way, from this side. But then I have to move this x over, so that means I'm also going to add x. Alright, so that adds to 0 and that adds to 0. So I'm left on this side with x, y minus 2y, and I'm left on this side with x plus 1. Alright, so to solve for y, I need to factor the y out. Okay, and then I need to divide both sides by x minus 2. So I end up here with y equals x plus 1 over x minus 2. Alright, so I'm just going to come up here. So that means that f inverse of x is x plus 1 over x minus 2, and then I just have to put the condition here, right? X cannot be what? Well, what's going to make that 0? It's going to be 2. Alright, so that is inverse function.